Alright, let's get this going. Alright, well, hello everyone. Welcome back to, this is now Programming Challenge, not OpenGL. However, I think we will be able to use what we're doing here in OpenGL, which will be pretty cool. So let me just pull all my stuff up, and then I just need to, I need to create the folder, and also I'll just be a second here. So 26, and today we're going to be looking at AVL trees. And AVL stands for Adelson, Velsky, and Landis, who are the, you guessed it, the creators of this algorithm here. And in general, AVLs are an extension of a binary search tree, and it's just a self-balancing variant that allows for much faster search times on average. So let's go ahead and let me just make sure I have everything set up, and then should be good to go. Okay, and let me, alright, this looks good now. Yeah, alright, we're good. Or are we? Yeah, okay. So we'll start in OneNote, and we'll first look at the binary search trees, so the BSTs, and how that algorithm is designed, and then we'll kind of translate that stuff over to an AVL. So, as you probably know, binary search trees, they are based on the concept of just kind of automatically sorting values as you insert them. So if we were to insert a 3, it would become the root, and then if we were to insert a 2, it would go on the left of the root because it's less than, and if we were to insert a 5, it would go on the right because it's greater than, so on and so forth. So insertion is pretty simple there. Once again, that principle of everything to the left of a node must be less than it, and everything to the right of a node must be greater than or equal to it. So if we were to have a larger tree, and I'll just go over the deletion operation because we're going to need it. Once again, insertion is pretty simple. So if we were to want to delete, let's say we had a 1, and then like that. So if this is our binary search tree and we wanted to first delete, let's say let's actually go ahead and do this. So if we wanted to delete, let's say the 1, since it's a leaf node, we can just simply remove it. So the resultant is just this here. So that would be that. Let me actually just put another one over here. Oh, that's not right. Let me just modify these numbers so the example will work. So when we deleted the 1, we could simply just free up the memory, or just remove the node from the tree, just simply because it does not modify the integrity or destroy the integrity of the tree. It still works as a tree. However, if we were to want to delete, say, the 2, so if we want to do a -2 here, the difference now is if we can't just remove this node, because then this 3 is attached to nothing. It's almost like it doesn't exist. However, we want to keep that 3 in there. So if we were to delete a node that has 1 child, all we have to do is just substitute it with the child. So the 2 goes away, and then we just store the 3 with whatever children it has into the 2 node. So the resultant is going to be the 4 at the top. Then the 3 is replaced there. And then the 6, 5, and 7. Just like that. Now if we wanted to delete, let's say, the 6, once again we can't simply delete it because it has children, so we have to figure out what to do with it. Or let's actually go ahead and delete the 4. That's a little better example. So we can't simply delete the 4 because it has children. So what we're going to do now is, since it has both children, it doesn't just have one child. So the order in which that we apply to this or the algorithm here is a little different from just substituting, because if we were to substitute it with, say, the 6 or the 3, well, the 3 would work, but if we were to substitute it with the 6, that wouldn't really work because it has 2 children. So putting the 6 up top would now give 3 children in the tree, which is not a binary search tree anymore. So what we're going to do is we're going to find the in-order successor. So we have the 4, 3, 6, 5, and 7. And what this is going to mean is we're going to take the in-order successor, so the element of the tree that is the smallest element of the tree that is larger than the 4 here. So all we can do there is just go 1 down to the right and then just traverse down the left side of the right subtree here. So we go here first, and then we continue going left until we hit a leaf node, which is the 5, and then we substitute up the 5. So it becomes a 5 up here, 3, then 6, 5, and 7, and then since we substituted this, we now need to recursively delete it. So -5, and that simply just gets rid of the node because it's a leaf node. However, if it had children, you would apply the same algorithm to delete the node. So yeah, that's basic binary search tree, insertion and deletion. We're actually going to be using these, except we're going to have a twist here. With an AVL, the goal of the AVL is to get the minimum average search time in a BST. So it's still going to follow the same sorting algorithm, where anything to the left of a node must be less than, and everything to the right of the node must be greater than or equal to the node. So as a result, what we're going to do is, it's still going to follow that, but the modification here is we need to figure out what's the best way to keep that the average search time is the smallest. So with the binary search tree, you can imagine that the average search time of something that looked like would be awful. It would be really high, because if we wanted to find the 100 here, we would have to go to the right, then 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 keep going to the right, and it becomes a linear operation. But in a balanced binary search tree such as this one here, that search time is reduced to log of n, where log is it's just that the maximum is the height of the tree, which is actually log of n. So the height here would be log base 2 of n, which is 1, 2, 3, 4, 5, 6, 7, which is equal to log 2 of 7, which is equal to 3. And we're gonna round it up, so like that, just like that. Whereas something like this will have a height of n. So the average search time will be, I don't know, n over 2, I think. Yeah, that's right. So what the AVL tries to do is it tries to dynamically rearrange the tree to make it a balanced binary search tree, or as close to a balanced, balanced binary search tree, but it's not exactly a balanced binary search tree. So with AVL, we don't get this straight lineage here. It tends to go away from the incestual family tree, where it would take something like this, and if we had, for example, a 4 and a 6, this is a perfectly good AVL. It's a valid AVL. And then if we were to insert the 7 now, it doesn't like this anymore. So what we would do is we would then perform some operations that would make it a 6, 4, and then a 7 like this. So the way it does this, or the way the algorithm is designed to detect these events, is it stores a height value with each node. So the height is just the longest path from a leaf node. So here we would have the height of this leaf node is 1, and then the height of the 6 is 2, because it goes it's 1, 2. So it's the longest path plus 1. So 1, 2, and then the 4 has a 3 here. And if we were to have, say, a 0, this height would still be a 3 because it's the maximum height. So that if we were to count the height from the 0 to the 4, that would be 2, but it becomes the max of the 3 and the 2, which is equal to 3. And the way it detects if something needs to be balanced or rotated, as it's going to be referred to here, is based on the difference or the weight of the the heaviness of the tree. So in this example, we define, or just in general, we define heaviness. So let me just make sure I'm getting this right. So we define the heaviness, or the balance factor, the heaviness or the balance factor as the height of the left subtree, so HL minus HR. So in this case, it would be 1 minus 2, and we just take the height from the left, the root of the left and the right subtrees respectively, and we get a -1. So this is perfectly valid. Once again, this is valid. However, there's whenever this balance factor, I'll say BF, when the absolute value is greater than 1, then we want to rotate it. Then we want to fix it so that it then becomes close to balanced once again, where the balance factor is indeed between -1 and 1. So yeah, we're going to be looking at that, and I'm just going to go through the 4 possible cases of how we're going to need to deal with or fix this, per se. So 4 cases here. And these apply to both insertion and deletion. So these cases can happen if you insert something or you delete something, anything that would make the tree unbalanced. So if we were to have the first case is called left-left. This means when the tree is left heavy, and this refers to when the balance factor is greater than 1. So the height of the left subtree is more than 2, is at least 2 greater than, wait, that doesn't make sense. The height of the left subtree minus the height of the right subtree is greater than 1. So the difference is at least 2. So it's left heavy, and then, but this also means that, or the second part of this case is that the left subtree is also left heavy. So that refers to something like, so let's say we had these nodes. Once again, this is balanced. And then if we were to insert something, this is not balanced. And hold on, I just need to make sure I'm doing this right. I want to get the right cases. this, yep, that's good. Yeah, like this. So the left subtree here is left heavy. And this over here, this left heavy right here means that it's super left heavy, or the balance factor is greater than 1. However, this left heavy over here means that the balance factor is greater than 0. Just that there's more nodes on the left side. So all we're going to do is we're going to perform a singular right rotation around the root node. So let's call this X. So we right rotate around X, and what this gives us is we have X with its child, and let's call this Y, or let's call this 1. So what we're going to get here is the result will be this. And now the heights are normal. So once again, we have a height of 1, 2, 3, 4, and then 1. So the height of the left subtree is 3, whereas the height of the right subtree is 1. So that difference is greater than 1. So we need to right rotate. Second case is going to be left right, where the left heavy, or super left heavy, and the left is right heavy. So it's kind of somewhat of the opposite of this, where let's say we had our X as our root, and 1, like this. Once again, this is valid because the height is 2 and then 1 on the left and right. And then if we were to insert something on, let's say if we were to insert, this isn't even you know what? Ignore these numbers real quick, just because I was just putting them to label them. I'll just fix this real quick. Yeah, like that. God damn it. Hold on, hold the phone. Alright, so let's say we had this, and then we inserted, say, a 5 now. So once again, we calculate the height, so 1, 2, 3, then 4, and then 1. So 3 minus 1 is greater than 1. But now the left subtree is not left heavy, it is right heavy, because the right subtree has a greater height. So what we're going to do now is, instead of performing a 1 rotation, we're first going to left rotate around 3. So we want to balance this one. Yeah, so this is going to give us X so this is our left rotation around 3, but notice now that this is still unbalanced, but this looks familiar because this is the left case. So all we need to do now is just perform a right rotation around x. And then from this we will get a 4 x 5 7 then 3 and 2, and it's balanced once again. Now the other two cases are going to be right and right left, but those are going to be exactly symmetrical to these cases. So for the right we're going to do one left rotation, and then for the right left we'll do a right rotation around the right, and then a left rotation around the new root there. So it's pretty symmetrical, which is cool. So yeah, let's I guess we can hop into the code now, because once again this procedure is the same if we're doing a deletion or insertion, because the same unbalances will arise in either case, and you deal with them in the same way. Okay. Alright, so let's hop into code here. I'm in Visual Studio Code right now, and I'm going to create 5 files. So we'll start with main.c, and in here I will just do our standard hello world, so include stdio.h, int main, printf, hello world, return 0, and then I'll have our batch files to run the program. So we'll have a run.bat, and then debug.bat. So run will be gcc -o a.exe main.c avl.c, which is a file that we're going to create. Or I'll just start with the main.c for now, and then a.exe, and then for debug it's going to be gcc -g -o a.exe main.c, and then gdb a.exe. So if we were to run, it doesn't like it. Okay. No, hello world. Alright, we're good. Alright, so let's create our other two files now, avl.h and avl.c. So we just need to add avl.c to the build path here, our batch files, so that it compiles the source file there as well. Alright, we'll start in avl.h. And we'll have some macros here. So hashtag if not defined, avlh, define avlh, and if. Within this if block here, I want to define a macro function, define max a and b, and this just is going to return, so in parentheses, a is greater than b, question mark, a colon b. We're just going to need this in comparison. Alright, now we're going to have our structure here. So type def struct avl. We're going to have a void pointer key, a void pointer value. Then, just like a binary search tree, we're going to have a struct avl pointer left and a struct avl pointer right, and then we will also have a key compare function. So int key compare, this is going to be a function callback, and takes in 2 void pointer keys. And then we will do a type def struct, and then just make it avl. So the difference between this and a BST node is that we need to store an extra thing. So when we looked at this in the comparison, we were relying a lot on determining the heights. Now, if we were to determine the heights each time we iterated through that, we would be wanting to find the maximum height of each node. And that in itself would be linear. It would be costly. So what we can do is, with the cost of a little bit extra memory, is we can store an integer value with the height here. So the height will be stored with each node, and then we'll update it accordingly. Alright, so I'll start with the allocation methods. So this returns an AVL pointer, AVL create root, pass in a void pointer key, a void pointer value, and an integer for just the callback here. So int, then in parentheses pointer key compare, and then in another set of parentheses void pointer val1 and void pointer val2, which are the parameters for the callback. And then we'll have another function, AVL pointer AVL create empty root, and this will just take in the function callback. So int key compare void pointer val1 and void pointer val2, and this will just allow us to create an AVL tree without any keys or values yet. Alright, so let me copy and paste these definitions. And the reason why I'm using a void pointer is so that it's generic. You can have whatever you want here. Alright, in avl.c we need to start with our includes, so include avl.h. And then for the first function, I just paste the signatures in here. Alright, so we'll have a placeholder here, so AVL pointer ret is equal to malloc size of AVL. So just allocate the memory. If not ret, return null. Just check to make sure the memory is allocated. Then we'll initialize the value. So ret.key is equal to key. Ret.val is equal to value. Ret.height is equal to 1. So each node starts out as a leaf node, so the height will be 1. And then ret.left is equal to null, and ret.right is equal to null. And then we also want to set the function callback, so ret.keyCompare is equal to key compare, and then return ret. For the second function, we are just going to call the first function, just passing in null values for the key and value. So return AVL create root, pass in null, and then the key compare callback that was passed in as a parameter to this function. So key compare. Alright, so this is allocation. We've seen this. I'm not sure what's the problem here. Identifier null is undefined. The fuck are you talking about? Alright, I don't think. I hope it doesn't cause a problem. Alright, next I will have the value function, or the utility functions per se. So these aren't, I'll call these accessor functions. So these aren't going to be utility functions because they're not going to be the operations, but these are going to be used to access the values. So we'll have a function returning an AVL pointer, and this is going to be AVL smallest key, and this is going to be taking an AVL pointer root. And this will be used to get the in-order predecessor, or in-order... Is it predecessor? Yep. Wait, no. Predecessor comes before. In-order successor. Yeah. And then we'll have a function returning integer, AVL height. Pass in an AVL pointer root. and then integer AVL balance factor, taking an AVL pointer root, and then a void function called AVL recalc height, AVL pointer root. And this isn't even an accessor function, but I'll put this with the operation functions. Alright, so I'll just put this down here. Alright, so we'll start with the top three. The smallest key, the height, and the balance factor. Alright, for smallest key, we essentially just want to determine if we're at a leaf node. And then just, if we are, then we return. Otherwise, we're going to traverse down to the left to find the smallest key. So return root.left question mark. So if the left pointer exists, if it does, then we want to go down. But if it doesn't, then we're at the smallest key possible. At the subtree rooted out the root parameter. So the first one, or the first return, will be AVL smallest key, recursively call on root.left, otherwise return the root. For the height, this will just be return root question mark root.height colon 0. This is just to remove the redundancy, or just remove all of the checks to see if the root height or if the root is a null pointer or not. So this will just check it in this function just to do it in a more simple manner. For the balance factor, like I said, it is going to be the difference of the height of the left subtree and the right subtree. So it's going to be return root question mark AVL height, we'll call that function using root.left minus AVL height of root.right. And then otherwise colon 0. So note here how if root.left is null, so now we're, come on, where's it? Let's say that we didn't have this 5 here, so let me just erase this. And if so, in X, root.right is null. So we call the AVL height function with the root.right, which is null, so therefore the function will return 0, which will just give us the height of the left subtree, which is a 3, which is pretty cool. Alright, so we'll be using these 3 functions pretty often. Alright, for the operation functions now, we're going to have quite a few. So we have recalc height, that's just the first one. Then we'll have AVL pointer, AVL insert, pass in AVL pointer root, void pointer key, and a void pointer value. And then we will have another function here called AVL return AVL pointer, and it's going to be called AVL underscore BST underscore insert, and this will take an AVL pointer root, a void pointer key, and a void pointer value. The point of this is just to separate the BST functions from the AVL extensions. So AVL insert will call, let me just zoom in real quick. AVL insert will call AVL BST insert to insert it through the standard BST algorithm, but then it will have those checks later on to balance if necessary. Alright, and then we'll have AVL pointer, AVL remove, pass in AVL pointer root, and a void pointer key. And then we're going to have an AVL pointer, AVL underscore remove toggle free, and this will pass in AVL pointer root, and a void pointer key, and a character free node. So here the character will just represent a boolean. So the purpose of this function is, by default, in the BST deletion, when we delete a node, let me just, so over here, or by default, when we delete a node, we just want to get rid of it. We want to free up the memory so it can be used elsewhere. However, in a case like where we're directly substituting in a key, then you know what? I think I'm overcomplicating this. Yeah, I think I am. Okay, I was thinking that since we don't want to delete this substituted node for the case where the node has two children, where we substitute, but I'm just realizing now that we can just copy and paste the values and then free or delete it and free the memory by default. All right, you know what, that was a stupid idea, but you know that's why we have that's the whole purpose of comp sci, because you can revise your algorithms. See, I was a dumb idiot 20 minutes ago, maybe a little longer than that ago, but you get the point. All right, so we can just make the second function be AVL underscore BST underscore remove. So this will just be the BST removal. And then we'll have our rotation functions. So return AVL pointer, AVL rotate right, pass an AVL pointer root, then AVL pointer, AVL rotate left, pass an AVL pointer root, and then AVL pointer, AVL balance, or yeah, just a rebalance, and pass an AVL pointer root. So the reason why all these functions are returning AVL pointers is because sometimes if we, so let's say we, in this case over here where we deleted the node, and we call remove for, or remove the root, or remove from the root node the key 5, or remove the root node, which is 4. So we call remove 4 as the root, and then 4 the key that we want to remove. However, that root node is going to be freed. The memory of the node that we deleted will be freed. So therefore, we want to return the new pointer to where that to the root node, which will be the 5 here. And then similarly, in this case, the root pointer may be updated. It all depends on the cases. All right, so let's fly through these real quick. So I'll copy and paste these signatures. All right, we'll start with recalc height, and then we'll work our way down. Or actually, let me move recalc height to the bottom, just because it's just to organize it a little better. And then we'll work our way from the bottom up. So we'll start with the nuts and bolts, and then we'll get to the more important functions. All right, for recalc height, all it's going to be is we're going to say if root, then we're going to say root.height is equal to 1 plus the maximum of AVL height of root.left and AVL height of root.right. So this is just the definition of the height, of the maximum height, and all we're doing is we're just taking the maximum of the two subtree heights and then just adding 1 for the current node. Let me actually move rebalance up above the rotations. Alright, now for rotate left. So this is going to be the rotation here, and it's a little more daunting. I remember when I learned this, I was shitting my pants just because I had to do it for an assignment and I had no clue what it meant, but it's just a simple few assignment variables. So the first thing we want to check is if not root.right, and just return root, because there are no rotations to perform. Can't rotate right or rotate left if there's no right node to replace as the root. Now for the substitutions here, we're going to have an AVL pointer new root, which is equal to root.right. So if we go to our cases up here, and we look at the right rotation, so the right rotation around, wait no, I want to see a left rotation. Alright, left rotation around 3. So we're just looking at around this subtree right here. So the left rotation, we're essentially going to bring the 4 up and move the 3 down. Just like that. So it's kind of just, I don't know how to, I don't have a graphic for this, but you're just kind of rotating the nodes so that it maintains its BST structure. Alright, so we get the new root, which will be the right child. And then root.right is now equal to new root.left. So here we have the new root, the right child of the old root. So this 3, if let's say this 4 had another child, like let's say this was a 3.5 over here, and then we left rotated, this would become 4, 3, and then we put the left child of the right child, or the left child of the right subtree over here, and then that also is the same there. So the purpose of this is just to maintain that structure, because if we were to, once again, if we just simply moved it up, it would have 3 children, and that can't happen. However, we can't just move this child down because we might run into other problems, but we know for a fact that the old root has space for a right child because its old right child is becoming the new root, its new parent. It's some weird family dynamics there, but yeah. So this link here between the 4 and the 3.5 vanishes, and it now goes to the 3. So that's how that works. And then we just say new root.left is equal to root. So we're just making the old root the left child of the new root. And then we want to recalculate the height here. So recalculate height. So AVL recalc height root, and then AVL recalc height new root. And if we didn't do this, what's the point of rotating it? Because the point of the purpose of rotation is so that we modify the heights so that it becomes a balanced BST. So we want to update those values in the nodes, and then return the new root. For rotate right, it's going to be exactly symmetrical. So we'll start with if not root.left, return a root. And then next we're going to have an AVL pointer new root, or as a placeholder, is equal to root.left. Then root.left is equal to new root.right. And then new root.right is equal to root, and then recalculate the heights. AVL recalc height for the root first, make sure you do the root first, and then AVL recalc height for the new root. The reason why we do the root first is because the height of the new root needs to take into account the new height of the old root. So we need to recalculate the height, the height of the old root before doing that. And then we return new root. Damn it. Ooh, this is the best. God, this. I'm going to turn this up a bit. It's so good. Okay, now for rebalance, we're going to use the rotation methods. So the first thing that we want to do is get the balance factor, because we want to determine if a rotation is actually necessary. So int bf is equal to AVL balance factor of the root. Now if bf is less than -1 or bf is greater than 1, then we have our 4 cases. And I'll just rewrite them here if you forgot. So our first one is going to be left, which means that it's left heavy. Left child is left heavy, or is balanced or left heavy. That's how we're going to consider it. And this one will result in a right rotation. Second case is going to be the left-right, so it's going to be left heavy, but left child is right heavy. Yeah. And I don't need to specify here that it's super left heavy, because it is already known, because the balance factor is already, the absolute value of the balance factor is greater than 1. So if it's left heavy, then the balance factor will be greater than 1, meaning it's 2, 3. So we know it's already super left heavy. And then the children of the root do not need to be super left heavy. They just need to be. It doesn't matter what they are. If they're super left heavy or left heavy, it only matters what type of heavy they are. This sounds so weird to say, what type of heavy. But yeah, which way they are heavier in. So like, let's say you had like you built all your muscles up only in your right side, you would be right heavy. And then you just padded up your left side just with a bunch of fat and Skittles and shit. Then you would balloon up on the left side, but that doesn't mean that the muscles would not outweigh that. So you would still be right heavy. So for second case, we perform a left rotation around the left child, and then now left case, so rotate right around the root. Then the third case is going to be right, so right heavy, right child is balanced, or is balanced or right heavy. It's going to be a left rotation around the root. And then finally the fourth case, right left. So it's right heavy, and then left child is left heavy, or right child is left heavy. So once again, just symmetric. So we're gonna do a right rotation around the left, or around the right child, and then now right. So rotate left around the root. Alright, so let's diagram these out. So we'll say if, first one is going to be case 1. So if BF is greater than 1 and AVL balance factor of root dot left is greater than or equal to 0. So these conditions are outlined in the comments here, but once again, BF is greater than 1 means that the left side is heavier, and then the balance factor of the left child is greater than 0, or greater than or equal to 0. So it's either balanced or left heavy. In this case, we're going to say root is equal to AVL rotate right around the root. In case 2, else if BF is greater than 1, we don't need to say balance factor is less than 0 because that's the only other case here. Since we know that since we know BF is greater than 1, we're still in that condition here, and we know that the balance factor is greater than or equal, or is not greater than or equal to 0, so it's the only other case here. So root dot left is equal to AVL rotate left around the left child, so root dot left, and then root is equal to AVL rotate right around the root. In case 3, else if BF is less than -1 and AVL balance factor of root dot right is less than or equal to 0, then root is equal to, alright, I'm going to turn this down now. So root is going to be equal to AVL rotate left around the root. And then the final case will just be else because we know that BF is less than -1. We know that for sure because it's not greater than 1, and we know from here that it's going to be less than -1 or greater than 1. So we've ruled out it's greater than 1, so it has to be less than -1, and then once again we know it's not less than or equal to 0, which means that it's greater than 0, so it's going to be left heavy. So root dot right is equal to AVL rotate right around root dot right, and then root is equal to AVL rotate left around the root. Alright, nice. And then in the and then outside of that, the whole if statement, we just want to return root. Alright, so that is, that's rebalancing, and now we're going to use these methods, all of them, to do our insertion and removal. Alright, so we'll start with removal, or, yeah, we'll just keep the pattern of going up. So we'll start with remove the BST version. Alright, so the first line here is we're going to get the comparison of the keys. So int comparison is equal to root dot key compare, and we're going to pass in the key 1, which is the key that we passed in as the target key that we want to remove, and then root dot key. So once again, the purpose of this is to determine if, or not once again, but the purpose of this line is to determine if the key is going to be on the left or the right side of the root. So if comparison is less than 0, then the target is less than stored key. So look left. So if root dot left, then we're going to go down. So traverse left. So root dot left is equal to AVL remove root dot left and key. And then we want to recalculate the heights. So recalculate heights. So AVL recalc height. First do root dot left. Once again, because it's a child of the root, and then AVL recalc height root. Now in the back in the I don't know how to say this, but the base if statements. So the highest level of if statements. That's it. The highest level of if statements. We're going to say else if comparison is less than 0. So target greater than stored key, look right. So if root dot right, traverse right. So root dot right is equal to AVL remove root dot right and pass in the key. And once again, the reason why we reassign them is because these functions will return the updated node that is now in the place of that if something changed, if the structure changed. And then AVL recalc height of root dot right and AVL recalc height of root. Alright, now in the highest level, again, we're going to do an else statement, so the target key is found. And now we're going to have our 3 cases. So the first case is leaf node, and as a result, we can simply delete. Second case has 1 child, so we're going to substitute with that child. And the third case will be has both children, so we're going to substitute with in order successor and then delete and then recursively delete the in order successor from the right subtree. Alright, so we'll start with case 1. So if not root dot left and not root dot right, so there's no it has no children, so we just simply delete. So hold the phone. Oh, okay. And then we're going to say free root. And then return null. Alright, second case. If root dot left and root and not root dot right. So this means that the only child is left. So we're going to say AVL pointer ret is equal to root dot left. Then we're going to say free the roots there, and then return the ret. So we get the left subchild, free the memory from the root, and then return that, the placeholder. And then else if root dot, or not root dot left and root dot right, it's going to be the other way around. So only child is right. So AVL pointer ret is equal to root dot right, and then free root return ret. And then case 3, we know that this is going to be an else, so we don't need to actually put an else because we return in all of these statements. So it's going to automatically go here. So we're going to get this substitution. So AVL pointer sub is equal to AVL smallest key of the root dot right. And then we're going to now copy the values over. So root dot key is equal to sub dot key. Root dot root dot value is equal to sub dot value, and then we want to recursively delete it. So root is equal to AVL or AVL BST. No, AVL remove. Pass in the root, and the value or the key, the target key, will be root dot key. And we actually want to remove this from root dot right. And then we want to recalculate the height. So AVL recalc height, pass in the root. And the reason why we don't need to recalculate the height in the first two cases is because the height of the substitutions will not change. We're freeing the values of the roots. So let me just go back here. For example, so let's say this was our tree. So I'll just put the heights. So 1, 2, 3. And if we were to delete the 2, what would happen is we just substitute with a 3. So that stays a 1. This becomes a 3, which stays the same because it's over here. But we're going to recalculate that anyway. And these all stay the same here. And we recalculate the height for the root when we recurse, or when we return from the function, because we're going to go down from the 4 to the 2, which will then, once we go back, it will recalculate the height, which is still going to be the same. Alright, and then after everything, we're going to return the root. Or you know what, we can actually just do one call to AVL recalc height outside of the if statements, and then delete the recalc height of the root in these methods up here, or in the first two if statements. Okay. Yep, so that's deletion. Alright, for the base method AVL remove, this is going to be pretty simple actually. So the first thing is going to be to remove as in a BST. So AVL pointer new root is equal to AVL BST remove, pass in the root and the key, and then we're going to rebalance if necessary. So new root is equal to AVL rebalance, pass in new root, and then return new root. Good shit. So it's just those simple two calls. We remove as if we were looking at a BST, and then we need to apply the AVL and maintain the AVL structure by rebalancing using the rebalance method that we wrote. Alright, for AVL BST insert, going to be pretty straightforward. First, we want to have an if statement, so if not root.key, that means that we have null values. And this may come from us calling create empty root here. So if there are no values here, then we just want to put the values in. So root.key is equal to key, root.value is equal to value, and root.height is equal to 1. And then return roots. Now, otherwise, we're going to say if root.key compare, compare the key and the root.key. If that is greater than 0, yep, so if the comparison is greater than 0, then the key is if this is less than 0, then the key is less than the root, so we want to go down to the left. So new key less than stored key, insert left. So if root.left, then we're going to traverse down. So root.left is equal to AVL insert, and pass in root.left the key and the value. And then otherwise, we're just going to simply create a new node because there is no node there yet. So root.left is equal to AVL create root, because it's essentially the root of its own subtree. And pass in key value and then key compare, which will be root.key compare. Alright, good shit. And then now in the highest level, we're going to do something similar for the right side. So else, so new key greater than or equal to stored key, insert right. So if root.right, then we're going to traverse down. So root.right is equal to AVL insert, pass in root.right and the key and the value. And then else, we're going to say just create a new node. So root.right is equal to AVL create root, the key, the value, and then root.key compare to pass on that the callback. And then outside of all the statements, we're going to say AVL recalc height, pass in the root, and then return root. And we don't need to worry about any about recalculating the height for the root.right, because that's taken care of in the recursion method here, in the recursive call to the method. Okay, so yeah, that's pretty straightforward, just a simple BST insertion. Now for AVL insertion, it's going to be pretty similar to AVL remove in that we're going to insert as in BST. So AVL pointer new root is equal to AVL BST insert, pass in the root, the key, and the value, and then rebalance if necessary. So new root is equal to AVL rebalance, pass in the new root this time, and then return a new root. So perfectly mirroring the AVL remove in that we do the procedure as in a BST, and then we rebalance. Alright, good shit. So those are all our operation methods, and we're actually doing pretty good on time, I think. We just have a few more methods that will just be helpful to allow us to play with this. So we'll start with traversal methods. So AVL, or void AVL in order traverse, pass in AVL pointer root, and then a callback to a visit function. So void, we'll call this pointer visit, and then the parameters will just be an AVL pointer node, and then this will be similar for pre-order and post-order traverse. And I will talk about what these are once we get into the coding. Alright, just like that. And then the parameters stay the same. Right, so let's copy these signatures. And we'll go top to bottom. So for in order, all it is we essentially go in order of the keys. So since the BST is dynamically sorted, all we have to do is just go to the left side, visit all the nodes there, then visit the current node, and then go to the right side and visit all the nodes there. So here it's going to be if root.left AVL in order traverse, where we're going to recursively call this method root.left and then visit, same callback function, and then visit the root, and then if root.right AVL in order traverse, pass in root.right as the root node, or as the new root node, and then visit. Alright, for pre-order, we're going to first do the children and then the root. So if root.left, then AVL post, or AVL, wait, sorry, that was wrong. Pre-order is visit the root first and then the children. Just confusing them. I had my reference the other way around. So pre-order means that the root comes before, so pre. So you visit the root first, and then if root.left, AVL pre-order traverse, pass in root.left, and then the same visit function callback. And then similarly, if root.right, AVL pre-order traverse, pass in root.right as the new root, and then visit as the same callback. And then for post order, now it's going to be the children first and then the root. So if root.left, AVL post order traverse, root.left and pass in visit, and then if root.right, AVL post order traverse, root.right and then visit, and then visit the root. So the importance of post order traverse is that we're going to use this for the deletion because it visits the children first and then the parents. So we want to free the children before freeing the parent, because otherwise the pointers to the children are just lost and that memory stays allocated. Alright, those are traversal methods. And then now we're going to have our freeing methods. So we're going to have a void AVL delete node, pass an AVL pointer node, void AVL delete node deep, pass an AVL pointer node, then void AVL free, AVL pointer root, and then void AVL free deep, pass an AVL pointer root. So the difference between freeing and freeing deep is that when we free deep, we want to also free the pointers to the key and the value. So we'll start with delete node, which simply just calls free node, and then delete node deep we'll call free node.key and free node.val, and then after that free node, now AVL free is going to be the AVL post order traversal of the tree rooted at root, and the visit function will be delete node, AVL delete node. So once again, we're doing the post order traverse to visit the children or delete the children first, and then we want to delete the parent. And then free deep will be the same thing. So AVL post order traverse starting at root, and the callback or the visit function will be AVL delete node deep. Alright, nice. Last two functions, and then we'll do some testing. These are just going to be some default key comparisons. So we'll have an integer string key comparison, pass in a void pointer key 1 and a void pointer key 2. Make sure that these are void pointers because we want to match this parameter list to the key comparison callback in the AVL node structure. Alright, for string key comparison, we're simply going to call the string comparison function, so strCompare, of the character pointer of key 1 and the character pointer conversion of key 2. And then this reminds me that we did not do any includes in the top of this. Or wait, why am I doing this here? Oh wait, sorry. Leave this definition until the source file. And then we'll have something similar for an integer key comparison. So return type int and int key comparison. Pass in a void pointer key 1 and a void pointer key 2. Alright, now I'm going to copy and paste the signatures. Alright, so we have to have our includes up here in avl.c, so we need include stdlib.h just for the memory allocation, so malloc, and then include string.h for the string comparison function. So for the string key comparison, we're going to use the string compare, so return str compare, passing in the character pointer conversion of key 1 and the character pointer conversion of key 2. And then for integer key comparison, we're first going to convert them to integers, so int I1 is equal to the dereference of the integer pointer conversion of key 1. And then similarly for I2, which is going to be the dereference of the integer pointer conversion of key 2. And then if I1 is greater than I2, return 1. Else if I1 is equal to I2, return 0. And then else return -1. Okay. Alright, so now that that's all our functions, let's go ahead and test this out. Let me just get the... I'm going to get some images of examples that I want to show you guys. So just let me get these up. Come on, where's the image? Come on, I need to find it. No, that's not it. Here it is. Is this it? Yeah, this is it. Okay. Let me actually just reorganize my window so you guys can see this example. All right. Okay, so let's hop into main.c, and we will we'll start by first including the AVL header file, like so. Did I remember to fix this? Yeah, I did. Okay. So we're gonna have a function here just to print out the AVL pointer nodes here. And this is just going to print out a bunch of values. So we'll have it printf. I want to have it print 1, 2, 3, 4, 5 integers here. So %d, %d, %d. Then we'll print out the left one. So left L %d and then R %d. You don't need to do this. I'm just doing this to show for illustration, and then I'll just have a few of the values here. God, this D, god damn it, just gonna print out the left child now, sorry, the left child's key. So node.left.key, that or -1, and then node.right, same deal. Perfect. Doesn't like this. Ruh-roh. What does it not like? I have a semicolon. Oh, I have two unbalanced parentheses. Alright, so we'll have an integer value here. So this is... so we'll start with the insertion examples. So we'll start a quick tip here. If you want to kind of follow these examples, and if you want to just follow your some examples that you wrote either by hand, and you want to mimic the structure of these BSTs, all you got to do is just do essentially a pre-order traversal of the tree. So you start at the top, you write the numbers, then so we're gonna do 13, then you go level down and just go horizontally, so top to bottom, left to right. So we'll have an integer array of values here. This is going to be equal to 13, 10, 15, 5, 11, 16, then 4 and 6. And then AVL pointer root is equal to AVL create empty root. Pass in the integer key comparison. That's a comparison function we want to use. Then for int I is equal to 0, I is less than, we have 9 nodes in here, I++. Root is equal to AVL insert, pass in the root. So this will give us a balanced tree. Our AVL insert pass in, I'll say vals plus I and vals plus I. So the key and the value are going to be the same. And then we'll have an integer value 14 as the value to insert. Then root is equal to AVL insert root, and then a reference to val and a reference to val. And then AVL pre-order traverse, and we're going to pass in the root and then print as our function. And then we want to print out, then we want to go free the tree. So AVL underscore free and pass in the root, and then printf done. Like so. Okay. Let's run this. Oh, I didn't put a new line. Alright, so let's see what we have here. So we have a 13 as the root, then that gives birth to a 6. Oh, fuck. This is no bueno. God damn it. Alright, is this... Let me try printing it without the insertion here. Just see if that's right. Because that could be the case. Alright, 13... did I put the values in wrong? No, 13, 10, 15, 5, 11, 16, 4, 6. Oh, god damn it. Let me check to see if it's unbalanced anywhere, or if, because it should be completely balanced in these insertions. So we'll just say if AVL balance factor of new roots is greater than 1, I'm just trying to print out where it's rebalancing, if it is. Oh wait, this is in remove. I want to put this in insert. Alright, so let's run this. Oh, alright, 1 second. I just need to include the standard I/O. Rebalance on add 0. Don't add 0. Just oh, okay. I think that's the when we're adding 0, that is the oh fuck, what is it? The root or the empty tree. But this still shouldn't change anything. Insert 0. Did I? What? There are 9 values here, correct? 1, 2, 3, 4, 5, 6, 7, 8. Okay. God damn it. Alright, now that should work. Alright, yeah, that was just my mistake there. Okay. Now I want to get rid of all these print statements. So if we run this, we should get that 13 is a parent of 10 and 15. 10 is a parent of 5 and 11. 5 is a parent of 4 and 6. 11 is a leaf. 4 and 6 are leaves. Then 15 is a parent of 14 and 16, which are both leaves. Perfect. I'll zoom in once again just so you guys can see this. And then I'll just do one example for the deletion. Or wait, you know, I didn't even show you guys that did the rotation properly. So let me do this here. So we'll start with the same tree. So 13, 10, 15, 5, 11, 16, 4, 6, and then we insert a 7 now. And we get that 13 is a parent of 13 is a parent of 6 and 5. 6 is a parent of 5 and 10. 5 is a parent of 4. 4 is a leaf node. 10 is a parent of 7 and 11, which are leaf nodes. 7, 11. 11 is a leaf node, like I said, and then 15 is a parent of 16, which is a leaf node. Perfect. Alright, one quick example of deletion, and then we should be done. So we have the new values are going to be 44, 17, 62, 32, 50, 78, 48, 54, 88. And then this is now 1, 2, 3, 4, 5, 6, 7, 8, 9 values. Alright, just need to make sure that's good. And then the value we want to delete is 32. And then we're going to say AVL remove. And we want to remove the 32. Alright, let's run this quickly. Let's see. So we have that 62 is a parent of 44 and 78. 44 is a parent of... fuck. God damn it. So it seemed to delete the 17, but why would it delete the 17? Son of a bitch. Alright, let me just make sure that the structure is proper before we delete it. 44 parent of 1762, 17 parent of 32, 62 parent of 50 and 78, 50 parent of 48, 54, and then 78 parent of 88. Good. So that's right. Now AVL remove. Let me do a quick thing here. Just gonna print out where we rotate. LR around 44, that's right. Okay. But, maybe I told it to delete the wrong thing and remove, maybe? Here we go. So case 1, leaf node. Case 2, only child is left. Our case here should be that it's both. So we want to, yeah, this has both. So 32 is, no, 32 is a leaf node. All right, I'm gonna whip out the debugger. This is step in. Okay. Let me actually just, let me do this before I rebalance. I want to see if it's, if that helps at all. So I can identify where the problem is. Okay. It seems to be that the problem is that it's deleting the wrong node. Can't determine why. Because that's working properly. Okay, so it's not the rebalance, it's the remove. Okay. Alright, step in. Oh god, print compare. So the comparison is -1 because we want to remove the 32, which is less than the 44. All right. So we want to go to the left now. All right, step in. Next, print compare. Compare is 1 because the 32 is greater than the 17. So next. Oh, okay. Jesus. I know. Oh, son of a bitch. I see what I did here. So in the comparison, I said if comparison is less than 0, and then comparison is else if comparison is less than 0 again. Never did greater than 0. Okay. So once again, if the comparison is greater than 0, we want to go to the right. So now let's run this. 32 is gone. It's now 1750, which sounds right. Yep, 62 was a parent, gave birth to 44 and 78. And then 44 is the parent of 17 and 50, but 50 is the illegitimate child of 44 because it's originally the child of 62. And then 50 still has its children of 48 and 54. And then 78 has its child of 88. So fuck yeah. Alright. Good shit. Alright, I think that's it for me. Yeah, that's AVL trees. I might think I'm probably just going to incorporate this into the OpenGL project at some point. But it's not a necessity right now. But yeah, maybe I'll do another video this week, but it's unlikely because I'm in the midst of studying for midterms. Just gotta get through Saturday, and then should be good. And then I got a week off, so I'll be able to do some more stuff next week, which is awesome. So yeah, hope you guys enjoyed this. Hope you learned something, and stay safe. And I will see you later.